Hello, everybody. As you know, the four-bar linkage mechanism is basically made up of four members. Three of them are moving, and one of them is a fixed link. And you might call them like input link, the con rod or connecting rod, the output link, and the fixed link or ground link. And I'm going to show the size of them here, the length of them by A, H, B, and G. Now, one of the things you probably have seen with this mechanism, it can do different types of motion. For example, the input link can do full rotation, but the output, depending on these different sizes of these members, it can only go between two angles. We call it rocker motion, or it can also do full motion and so on. So you might wonder under what conditions these different types of motion exist, and that's what we're going to discuss today, which are called the Grashof condition for four-bar linkage. So, and before I go to that, I just want to give you a couple of examples in real life. So here, like when you are biking, right? The input here comes from your thigh bone and the output is on the pedals. And you know your thigh bone only goes between two angles, but the pedal goes full rotation, right? That full rotation, we call it the crank motion, okay? So crank means full 360 rotation. And the oscillation between the two angles, we call it rocker. So crank, rocker, that's this mechanism. And there are other scenarios for rocker. I mean, the rocker is an oscillation between two angles, but none of the two end angles are 0 or 180. If it can go through one of those angles, but not the other one, so for example, goes through 0 degrees, but not 180, we call it zero rocker. And if it can go through 180, but not 0, we can call it what? A 180 or a pi rocker. So again, the main question is under what conditions these different shapes, different types of this mechanism can do the job. So as I showed you for biking, we had the input link to rocker and the output member to crank, right? So this is good for what? For a bike. On the other hand, if the input member does the crank, the output does the rocker, so the input member rotates constantly, but the output just oscillates. You can see that, for example, here in this mechanism for oil extraction, right? You see the input is attached to a motor and it can always rotate, but the output, which is this member, really needs to just go up and down, right? Or let's say when you are, for example, if you use it in a windshield wiper, the input is just what? Rotating constantly, but the output only does a rotation to make the windshield wiper go. Okay, so this, as I said, this one you can have in like oil extraction or for windshield wiper and stuff like that. So extraction. And if it's crank, that's what you see in like train wagons, right? In train, you see these are these tires, and then they are attached with what? With a link like this. So the two other members are these two radii. In this case, the ground member is just a fixed distance between them, so we call it a parallelogram mechanism. That's where the size of the two opposite members are equal. That's crank. So how do I know? This comes down to three values that you need to calculate, T1, T2, and T3, based on the size of the input, output, ground, and the con rod members, which I call them A, B, G, and H. So we calculate these three values, where in each one of them you see two values are added and two values are subtracted. And then depending on the signs of this T1, T2, T3, you can have different what? Different scenarios. Here you see 8 different scenarios. By the way, the source of all of this material is Wikipedia. So, first thing is, under what condition you can assure that one of the members can fully rotate. So when is it that one member can always crank? And that is called the major Grashof condition. As you can see, It says it happens when sum of the shortest and the longest links is less than or equal sum of the two other members. If that's the case, then the shortest member can do a what? Can do a full rotation. But in general, if we want to classify it as one of these different scenarios, we need to look at the signs of T1, T2, and T3, which I'm going to show you. And by the way, you might say, what happens if one of them is 0? In that case, the mechanism will fold, okay? And that's a separate scenario. But right now, let's take a look at different examples here and see different types of motion. The first one we're going to see is this one. All three numbers are positive. So the mechanism is a crank rocker. That's the first thing we're going to look, is all three positive. So the input is full rotation, the output is oscillation. And here I made them in SolidWorks for you. So here A is 6, B is 7, G is 9, and H is 8.5. And I calculated for you all of these three T's. I mean, just the sign of them, you clearly see that is like 17.5 minus 13. This is 16 minus 14.5, and this is 15.5 minus 15. So all three are positive, and if I move this mechanism for you, you clearly see the crank rocker. So this is my input. Look, it does full rotation, and this is the output. If you look at the yellow member, it only goes between two angles, but the green goes full rotation. And what are the two angles really? One of them is when this input and the conrod align. Look, so this is one. This is the maximum angle on the right side. Okay, this is one of the endpoints. The other one, again, these two align, but with a pi, angle of pi. So they become like this on the top of each other. This is the lowest angle on this side. And clearly you see that none of these angles, the left one or the right one, are what? 0 or 180. Okay, so in this case, it's a crank rocker, but the rocker is not a 0 rocker or a pi rocker. It's just a regular rocker. Okay, so this is what? This is one scenario. Now, if I go ahead and change one of these numbers, what happens? So, for example, if I go ahead and make this a 10, right? If I make this guy a little bit longer, so I make it 10, what's going to happen? Well, wherever I have 6, I have to go back and make it 10, see what happens. So let's go in and change 6 to 10. So if I make this 10, that's going to be 17.5 minus what? 17, so that it stays positive. This one is going to be what? Is going to be 16 minus 18.5, so that goes negative. And this one is going to go 15 minus 15.5 minus 19, which is again what? Negative. So you see, if I make the input link a little bit longer, make it 10, which I'm going to do in SolidWorks now, I should get first one positive, the second and third one negative, which is this scenario here. So you're going to get what? Rocker crank. So in this case, the input will rocker, the output will crank, which is exactly what you have in bike. So all I need to do is to go back here and look at this input member and modify it and make the length of it what? 10 instead of 6. So here we go. Double click here and change it to 10. And since I have the constraint, it will automatically update. There we go, right? So now let's see what happens if we do it again. So this time, this is my input. Look what happens. You see here, it locked already, and it also locks on this angle. So look, let me turn this one. Maybe it's clear to turn the output in this case. Look here. Look at the output is going full rotation, but the input is only doing a rocker motion. So this is the rocker crank instead of crank rocker. Finally, let's say we want to look at crank, this one. So for crank, the first two have to be negative and the last one should be what? Positive. And here I have changed these numbers. So I made A10, B 9.5, and then H still 8.5, and G 7.5. And if you look, the first two are negative, and the last one is what? positive. So in this case, it should do crank, crank. Both should fully rotate, and let's see if it does that. So here we go. There we go. You see here, both members do full rotation. Okay, so these are different scenarios to get different outputs out of the mechanism for different applications. Hopefully this video was useful to you, and I'll see you in the next video. Thank you.